All right. So welcome everybody to the last webinar in our series on building bridges in computational science, computational and data science. I'm Kate Cahill. I'm at New Jersey Institute of Technology, and I'm part of the Computational and Data Science Exchange project. And so this webinar is part of the beginning of our project to kind of bring people together to discuss computational and data science curriculum, and the webinars that we're sharing in this session are mostly from our project partners from our pilot project and the work that they have done developing this curriculum and sharing it amongst the members of the pilot project. With the new project, we're looking to expand our the exchange reach and broaden this group into a larger faculty of community of practice, so that we can develop more computational and data science curriculum and share strategies and tools for getting more computational and data science into classrooms. And so, as I said, today is our final session of this webinar series. So definitely look out for future announcements from us for future webinar events. But today we're going to hear from our project partner, Dr. Dina Tandabani, who from Clark Atlanta University, focusing on his work with computational chemistry and biology and science gateways. All yours, Dina.
Thank you, Kate, and thank you all for joining for today's webinar. The title of my talk today is Science Gateways as a Classroom Resource for Computational and Data Analytics Tools. One of the tools that I used, the Gateways resource, which I used in my class, is the C-Grid for Computational Chemistry and Molecular Modeling courses, which was effectively used in the classroom for the students, undergraduate students in chemistry and biology at Clark Atlanta University. I'm a professor of chemistry. The history of this project, it started almost like 8 years ago, when I came to Clark Atlanta University, which is a small private HBCU. Students do not know computers can be used for science. Computers can be used for studying chemistry, biology, engineering, physics, right? So I started developing a project proposal, which was successfully funded for developing a course. One is Introduction to Computational Chemistry and Molecular Modeling. Another one, I also helped my biology colleague to develop parallelly a course for computational biology and bioinformatics. Again, both of them are intro level, and students should be in their third year or fourth year to take these courses, because we want them to know at least some calculus and some chemistry, which is particularly the organic chemistry, because if they do not know the molecules, organic chemistry as well as the biology, some biological molecules, for them to learn and understand the structures, properties using computers. So that's a motivation. It was successfully developed and implemented. Then we joined as a project to make this course to be available to the other institutions. That is our pilot project. Now we want to expand to even more institutions, the computational and the data science. So why do I have to do this? If you want to ask me a question, why do I have to do that, right? And improve the curriculum. Always we are looking for to improving the curriculum. And use of technology, everybody is using. And I want to say that a better use of technology in content delivery, right, effective academic support and the student success, which are essential for increasing the number of undergraduate students. And my focus is now increasing the number of undergraduate minority students. Many times they are not really the numbers which we want or we want to increase. So we want to do something to make them interesting and attractive, their subjects, and get more motivated and get thrilled by studying, then successfully graduate and get ready for the job or the higher education. This is the goal. And now everybody is having the phone, right? Phone is also a computer. Actually, if I want to use some computing on my phone, I can do it, but I don't do that because I don't want to keep my phone like more hot and vibrated, because it can't handle it. But I can do small jobs, small calculations, right? But we can use any device right now to do the computing, right? So computation is now regarded as an equal and essential element, along with the theory and experiment, in the advancement of scientific knowledge and engineering practice. So we want to implement the computation. Of course, in addition to computation in today's world, right? In the recent years, the data science, right? Data, right? What we have done the data, I from the time I have done my PhD and research, we know what is data means. We used to deal with 10,000 lines of information and data. Now that it becomes a million lines and even billion lines, right? Why do I say billion lines? Because I really have seen the data of billions when I was a Microsoft visiting professor and worked with Microsoft. I had an opportunity to see and learn something of what they are doing as a Microsoft visiting professor 2 years ago in 2022. Now, it is important for us as an educator, as a professor, as an instructor, to educate the next generation of undergraduate students to confront the challenges in computational and data enabled science. Anything if you take in today's world is like a data enabled, right? With the data, we should analyze the data, get the information, get the knowledge, and build from that, right? And make conclusions based on that. So we should prepare our students to that level. That's why we have a project funded by NSF called computational and data science. As I mentioned before, by the support of the NSF, I developed from the scratch, from nothing, right? I can say ab initio because we use ab initio techniques, right? From the scratch. Introduction to computational chemistry, molecular modeling in Department of Chemistry. And it's not only for chemistry students, it also focuses for biology students. In many institutions, when you look at the number of biology majors are much more than chemistry, physics, or math. Maybe if you combine all three departments, and you can see that even still, we can't match to this biology students, right? So what is this course? What is the brief description of this computational chemistry and molecular modeling course? This course is designed for 4 credit hours, and the course has a lecture and lab to introduce the concepts of computational chemistry and molecular modeling. Why do I say molecular modeling? Because if I go anything beyond chemical molecules, go with the biological systems, I can say like peptides, proteins, DNA, right? Base pairs, nucleic acids, right? So I want to cover all of them. That's why I say molecular modeling and their applications in chemistry and biology. Because without the chemistry and biology speak, we cannot produce many of the drugs. And a lot of people is needed still, pharmacologists and biochemists, and a lot of different areas, toxicologists, right? Those areas of expertise are needed. But the main two people, when you have to talk about the biologists and chemists, they work together on this journey. But chemistry people can work without talking to biologists for something else, like a material science, designing of new materials, designing of new batteries. As when I do it, still I may need the help from the engineers, and I may need the help from the physicists. Though I say the computational chemistry is a core area which can be applied to different disciplines too. I can do the biological models. I can do the nuclear chemistry models, food chemistry models. I can do the biochemistry models. I can do various different applications. I can make uh, uh, protein drug interactions. I can study that area. So the computational chemistry, somebody understands really good, can go a widespread areas of uh, areas of research, areas of uh, the questions we can address, right? So the main purpose of this course, we can't do everything here actually in just one semester. That's why it's a introduction, because the computational chemistry is really vast, it's very big. And in the last 2 decades, I can easily say you that there are like 100 different methods were developed, 100 plus density functionals were developed, right? And many of them we don't use, but we have to know which method should be used. And there are like I've been issued DFT, molecular dynamics, Monte Carlo methods, right? It's so many different methodologies, tools, techniques are there. We can't do all of them in one semester. It may take even after 5 years of somebody has done finished PhD, they may not know all of them what I'm talking about, right? So the main purpose of this course is to introduce some of the techniques used in computational chemistry and molecular modeling with some simple and model examples, right? How these techniques can be applied and can be used to study physical, chemical, and biological phenomena. When I'm talking about physical, specifically the strength of the molecule, right? Call it a boiling point, freezing point, right? One can calculate. So the course is intended to prepare undergraduate students for higher education on computation-based research in chemistry, biology, or engineering by introducing the concepts and techniques used in computational chemistry and molecular modeling. So they know how to do the analysis of small data. If they do not know how to do the small data, they cannot do in big data, right? Many times these computational tools are called black boxes. What it comes, somebody do not understand, then come to a wrong conclusions, or conclusions may not be good all the time, right? So it is important to understand the basics. And with the support of the NSF grant, I created a lab with these Mac computers. I started with the 2 or 3 computers. Then within 2 3 years, I fully built this lab with 18 computers. If in the next year, when we are planning to have a workshop, if some of you may have an opportunity to visit the Clark Atlanta University, and I may have some hands-on experience of 1 or 2 modules of the computational chemistry, right? Students really started liking it. So I really enjoyed doing this. over and over, maybe like 5 years I have done. During the pandemic, it was not easy, and I started thinking different way. Let me go with the supercomputers rather than the local computers, right? That's how I started going to the mm, gateways, science gateways, right? When you look at the computational chemistry, what do we do, right? Very simple. When we take a molecule, like it's a mathematics, right? Mathematics is heavily involved. And somebody asks, right, what type of mathematics do you apply? I can say everything, right? I can say everything. Okay, vectors, yes. Do you do the matrices? Yes. Determinants? Yes. Integrals? Yes. Differentiation? Yes. Partial differentiation? Heavily, right? And sometimes we use uh, um, double and triple integrals. So, but without computers, we cannot do that. And the local computers cannot handle beyond a certain limit. So I definitely need the supercomputers. I have an experience of using supercomputers at the different levels. I also use the Department of Defense supercomputers, which are highly powerful. They don't tell about how much powerful they are, and it's like they don't also tell to the world that how big and how powerful machines they have. But I used them, the specialized with the special permissions, with special clearances. So, but I always go with the simple systems, right? Water molecule, we all know that it's only three atoms, right? H2O. I start with that actually because very easy, right? Three atoms. After that, I go to the methane molecules, four atoms. Another four atom molecules is the hydrogen peroxide, right? We use them. You can see the structure here on the right side, right? HOOH. And we should define the molecule, right? Though we see the structure, that's what we used to do it long time ago. Now we don't even need to do this one. We can draw the structure by click the button. That the technology developed to that level. So this is the way we describe this molecule with this distances, angles, dihedral angles. If the students do not know how this is created, they do not understand, because it's when they draw the molecules, if you think that all the time it will be right, may not be, right? So one should know the fundamentals of how this is created. So I go with the simple systems, simple molecules. Then after that, I give them the opportunity to enjoy drawing the structures, visualizing the molecules. And you can see it's more than one ways one can define the structure of this molecules. This is called the Z matrix, the one which you're seeing in the bottom of the screen, the four lines, which is called Cartesian coordinates, right? I ask the students, okay, prepare this input file. I usually teach some other structures. But for example, ethylene or acetylene, linear structures of water. Water, first I start with the water. I ask them to do for this one. Then they should run the calculations using specific methods, specific levels, which we are talking. This is an ab initio method, what you are seeing here. Very simple, these things will take just a few seconds to run the calculations, even in the local computers. But you should have a specific software to run these calculations. And as I said, water molecule is a different level. You can see infrared spectra of water, glycine, and alanine. You can see glycine and alanine are the amino acid structures, alpha amino acids, which are building blocks of the proteins. So this is an IR spectra. So when we draw the molecule, run the calculations, get the total energy in terms of arteries. And one can get an IR spectra, calculate the IR spectra. And the experimental people, when they do the experiment, they can also get an IR spectrum. So computational results and the experimental results can be compared. And the experimental people get an X-ray crystallographic structures. They can get the information of the oxygen-hydrogen bond. They can get the information of some other bond, like a carbon-nitrogen, carbon boron, something like that, or carbon-carbon bond. We can also tell the numbers based on the computations, which not only helps the experimental people to confidently report the results. If we have the drawbacks, for example, some molecules, some systems, the methodology does not work, then we can say that this has a drawback, this has a disadvantage. We should not use for predicting these properties. For example, this basis functions, right? So these are the fundamentals of the methods, strengths and weaknesses, or advantages as disadvantages of the methodologies can be taught to the students so that they can be very strong at the foundation level. And this is a glycine molecule. Yeah, I tell you, students really enjoy drawing the molecule, seeing the molecule, because many times a professor say, glycine, what is a glycine? I don't know what is glycine. When they look at 2 dimension, they may not like it, I tell you. They came and told me after that, I think you have to give these models to students, right? Then I got some physical models and I gave it to my organic chemistry professors. I'm also trying sometimes helping the organic chemistry students come and to see the molecules when they really need, right? They can come to my lab, or I created another lab for this purpose. They can come and see in my lab these molecules. It's easy. Then I have spectra, and they can compare the results. They can, and also sometimes the students will become a graduate student. They can do themselves a computation and experiment, or they may have to work with some computational people, collaboration, and they should understand how their results compare with the computation. And as I said, I also introduced the students the supercomputers. It was not easy. It is very hard because they had to, with the undergraduates, limited amount of time, they study during the semester to the specific course, even though I have a lab, 3 hours lab associated with this course lecture, but still that's not enough. Because if the students do a small mistake, they stuck there, and we had to go and help. And as one professor, it's not easy all the time, particularly when we access the supercomputer this way, right? So this is a traditional way we do it, accessing the supercomputer using some medium. Here we use putty. Then we can that's how we connect to the supercomputer. This is expanse. This is today we connected to that machine, right? The another way of doing is actually from here also we can do this called a WinSCP. From here we can connect to the supercomputers, which are in different locations. I have access in my group, my university. We have access to San Diego and Pittsburgh and Texas, right? TAC. So we have access to the supercomputers from here, anywhere, from home, from lab, from anywhere, even from the coffee shop, right? It's not the matter. We create and we submit the jobs, we collect back. This is a very good terminal to do this one, because we can transfer from, you see here, the left side, what you see is the local computer. The right side, we connect to the supercomputer, then just drag from here to here, here to there. Easy, right? Then after that, you do what you want, right? But with the students, they do one of the important things, they had to remember a lot of commands that's accessing to the supercomputers. And accidentally, if they do after they run the calculation, for example, instead of doing something, moving, or they do RM, right? That's all. It removes the file from that. So whatever the time they spent to the supercomputers to run the calculations, and it's gone. The file is gone. We can't get back that, right? It's a one way. It's gone. So remembering these things, it needs a lot of training, a lot of time. It maybe I can do it for the summer research program, but in the course it was tough. I'm talking based on my experience of doing it one semester. After doing 2 labs, I switched back to the local computers. Then during pandemic, I cannot go to the lab because they stopped. Then I was thinking what I had to do, right? Then I went to the gateway, right? They also need to use these types of the batch files to submit the job, right? So this is very important to configure for that. It's a different level of expertise is needed. Usually we prepare that, we give it to the student, use that, change your input name, change your output name, done. Don't touch any other lines, right? Accidentally, if they press one extra line or one hash or one slash, then it won't run. It will give the problems. So the ScienceWay community, Science Gateway, this is for all of us, right? It's all of us. So National Science Foundation funded this big project, mega project to San Diego Supercomputer Center. So with that, they created a different gateways. Those gateway computers are also applying for the supercomputer time, and they win the supercomputer time for the proposals. They win their proposals for the supercomputer time, and they serve to the community. And they, most importantly, whatever I was talking about, using this Unix shell, the command prompts, typing those commands, all this hassle is gone by using this. We're going to use the web portal. It will be easy. That is the intention. We want to increase the number of people who use these resources. We want to see number of people who come to the computing and the data science, right? Because why do I say the data science? Even for Python, you can use that. There are specific resources available. Python, R, something else, Julia, those things also you can connect, you can use it. So the purpose is Science Gateway Group, right? E-science research. Yeah, of course we can do it. Everything we connect it. Then open community software. That's another thing. You don't need to install the software in your place. It is somewhere installed. But you should get an access. You should get the access some software. Again, I'm telling you, even though you get a Science Gateway, you can't access some specific software unless you have a license. You should purchase for your institution. I have some software like that because I should contact the service provider. Then I should tell them that I have a license, and they should verify with the vendor, whoever is the software developer. Yes, I purchased it legally. Then they will add me in that group. Only then they can access. That's for mostly for the research, not for the education. If you are focusing on the education, most of them are accessible, and many of them are open source. So open source codes, easy to do that, right? If you really want in your institution some software, I can also help you. If you are looking for, okay, this is my budget, is there anything I can do it with that? Yes, I can be of, I may help on that situations, because I used several softwares. I don't know, maybe two dozen different softwares, right? So many of the softwares I know, because I was trained a computational chemist, computational material science. And I turned myself into more of the materials, and I do materials for many different applications in my research. So in the cyber infrastructure layer, you can see different colors in this, right? So you can say complementary gateway components. That's important. Behind the scenes, you don't know many of them. That's specialists, computer scientists, computer engineers, they do these things, right? But these are complements, web/gadget container. Yes, we can access through the web. That's a user interface service. The user management, information services, and you can run the calculations, right? After you finish the calculations, you get back this. I'm going to show you at least one example how to do that, right? The purpose of this, as I said earlier, we want to increase more number of people, enabling and democratizing scientific research, right? We want many people to do that. And more importantly, the computational resources available. You don't need to create in your institution. There are supercomputers, somebody that it's like some other institution, they have a huge amount of resource, several $1 million, like 25, 30, $40 million invested already. And in addition, additional $5 million invested to purchase all the softwares. It was compiled. It's ready to use. Scientific instruments. Even they get some gateways, not only for the computational purposes, also for the experimental purposes, but they also use the data. They also create the computational power. Huge amount of computational power is needed for those instruments and the data. So for experiments too, right? And algorithms and models and archived data and metadata. That's again important. We want to keep all those data. It's not that today we are generating. If like 10 years ago, what I have generated, I should keep. That's what my research is. If I'm doing it, yes, I should keep it. Somebody is asking, I had to provide what information I should provide or I can provide, right? The knowledge and expertise, right? That's very important in order to use this science gateway, right? And that also develops, when you use the science gateway, it develops people's knowledge, right? Communities, universities, and academic departments. As I said, shared instrument facilities. Some of the instrument facilities are shared by maybe 10 institutions. Then I can run easily, making multi-site collaborations and virtual organizations, right? Right now we are doing it, actually, virtual organizations. You come from different institutions, we are meeting virtually, we are building, sharing our knowledge, right? Then businesses and services and small research groups, it applies for me because I have like 5-6 students, they are running the calculations. Mostly my grad students can able to handle the Unix shell, the WinSCP, gateways, all of them. But when I come, the undergrad students, I don't put them in the Unix shell in year 1 or maybe first semester, because then somebody has to sit next to them all the time. Whatever the mistakes they're doing, and we have to tell them, it takes a lot of time, right? So I put them in the gateway and let them practice, get some great feeling of running these calculations, see the structures, then slowly introduce them. Although by second year, they know how to do all those things, what a graduate students do it. Because when they move from that undergraduate to graduate level, they are expected to do all of them. So it needs about 2 years of training. So I generally keep like 1 year at least to my undergrad students, or maybe 2 years. How does this work basically, the gateway? I said Unix shell is gone. You don't need to worry about it. Web portal, that's what is the main goal of this gateway. You put the input, you enter all the information, then it goes to the supercomputer, it runs the calculations and gets the data, right, raw data. Then what happened in that, then you say, once the data is collected, now it says, are you going to do the post-processing? Somebody needs to do it, somebody doesn't need to do that. Somebody doesn't need to do that. For example, in my case, I don't do the post-processing in this gateway. So I go back. So for my answer is no. It comes back to that data to my web portal. I download it and I download to my local computer. then my students start working the post-processing here. If you're doing the post-processing, then for example, any kind of post-processing sorting, maybe you had to analyze the data and you had to create some images, get it? Yes. Then again, you come back. Where you put it, then you get back there, right? So you get back your output after the post-processing. This is a very nice, right? Very nice diagram. It explains nicely the process. As I said, I use the Science Gateway, which is the cgrid.org. You can see science and engineering, collaborate experiments with the models. Earlier I said, right? Predicted novel phenomena, design new materials, which I do it in my research. Then cgrid, what is their goal? Prepare more model inputs, which it's easy to do it because everything comes, questions asked, you answer it, it's done, it's creating. The input is created, right? So then manage simulations and data, analyze and visualize output. That's what I was talking about, the post-processing. Everything is doing compute and the data resource, right? And if you want, the link is provided here, right? So you go to this link and you can see it. There are features like a computational chemistry, molecular dynamics, structural mechanics, fluid dynamics, physicists use, engineers use, right? Want to use for different purposes. Right now looks like it's not very active. Maybe I'm not logged in, so that's why you may have to create an account, and your students can create an account. My students created an account and they logged in, they ran the calculations. Of course, this is a medium and they had the resources, but I want to preserve their resource. I told them I don't need your resource. Then I gave my project number. Then for my students, they added from my project the computer time. All my students used my computer time in this gateway. I explained you most of the things here, right? So I'm talking about this. Which software I use? I use the Gaussian. So that time I asked my students to use Gaussian 09 and optimization, which I showed you the water molecule something, right? So water molecule geometry optimization, create the structure and run the frequency, which means it generates the IR spectra. The method which I used this and basis set I used, and it automatically creates these numbers, the number of basis functions, all those things. Then this also generally it creates by itself. Job status is once it is done, the calculation is done. Otherwise, it says in progress. Then it gets back your calculated properties by end. After that, it provides all the information too. So it is also getting the information from your output file. So somebody has written the program there. So students won't mess up anything here. Once you check one calculation, if it is running correct, it is providing the data correct, it's done. Whatever the students need to get to that information, it is coming, most of them. If they want to go advanced level, one step further, they can train. So it made my life easy, right? Even today, I'm not running in for last 1 year because I had trained undergrad students, so they don't want to use this. They know they are more comfortable using with the transferring files and all those things. Moreover, they also run big calculations because sometimes this one has some limitation of 24 hours or something. So it is good for the students, classrooms, but when it goes to the research, it's not. Maybe you may have to have a separate queue or something. So the students access the bridges and Comet, because right now it's not the Comet, it is Expanse. It was that time students accessed both machines depending on what they want to do and also how busy the machines are. So I used to switch. That is another thing. And this is one of the ways how we are giving the input files, right? From our local computer, just to select, generate, okay, select the specific structure, open it, and which software I had to use on a gateway. I picked that software and what method, what software is that. You see here, so many softwares are available in this gateway, right? Then I had to enter the method as I said, the job described, right? So I had to enter the method, which theory I had to do, what calculation I had to do. You see, everything is just selecting. It's a web-based web portal. It's not that they may do any mistakes in typing in the Linux. No, you see here, even it is much more easier. It's some selecting here, right? And then once it comes additional advanced level, only maybe only if you want to give advance, otherwise most of the time simple job descriptions. Then the last one is a preview. You see here it generated. Actually, long time ago we used to write all those lines in the Linux shell, right? Then create the input file. Now it's a very easy with this process. So we can run those calculations, get the output file, done. It's a classroom. It's a very easy to do it. I show one example of computational chemistry. How can we use the gateways? You can find the gateways. You can contact the gateways to get what is in your area, right? And you can use the gateway for your purpose for teaching computational and data science. With that, I stop sharing and I'm very happy to answer any questions you have.
All right. Thanks a lot, Dina. Does anybody have any questions? You can unmute or type in the chat. It's up to you.
I'll be very happy to answer any questions.
Hi, thank you for your talk. This is Alam Tanuri. I was wondering, for example, if a math student with basic knowledge of chemistry, really like 101 course, would it be tailored for somebody who is interested into, let's say, dealing with data and getting data from chemistry from the chemistry or biology field where they have to deal with molecules, etc., and etc.?
Yeah, definitely. And because even they can do a lot of mathematical models for the computational data. Example, I create like 1,000 different molecules and I have the property. You can do the machine learning. If you know that this data and the chemistry and the mathematics people work together, and we can get a new information completely. And one can generate the new structure and with the new values of the properties, which will be like a much more faster. I don't even need to, when I have a huge data, the data that it learns from the data, and then the prediction accuracy of the prediction will be really really good with fraction of seconds. I don't even need to go for the supercomputers. I may have to test for a few, but I may not need to run another 500 calculations, right? That will be an amazing with the current AI, machine learning advancements. I'm looking for. We can think of maybe after 6 months.
I like to follow my question from the perspective of a chemistry student. You talked about, like, I don't know, Monte Carlo simulation, double integration, triple integration. So students from chemistry, all what they need to know is the understanding of what they mean and when do we use them, but they don't have to do the calculation by hand. Just you will provide them, or they will be provided with by a software, let's say area under the curve, like they know integration, so they use it without really going through the I would say the strong background required from a mathematician.
I'm sorry. I got it because the software is provided. The reason the course is taught, we are telling which software, which properties, which methods should be used and when, right? So the software, as I said, my course is really intense. I go from this and the hands-on, like I used to create like a 10 labs, then different molecules, diverse set of molecules, different properties. I used Gaussian, I used Spartan, and I also used the some other software, but I stopped for the visualization then because of both the Gaussian and Spartan. They were really good. Then I stopped using this. I don't want to introduce too many to the students. But the purpose is, yes, the students should know the basics, and once they know the basics, they can use, they can, but they may not be able to choose at when they're undergraduates. Even for the graduate students, that's why they're getting the training. Maybe when they're like graduating, about to graduate, they will know the PhDs, they will know exactly when and for what and which software they should choose.
Thank you.
Any questions? Any more questions? I exactly stopped in 40 minutes. So
Nice. So how many students do you have using the gateway for a class?
yeah, that time, two times I have done. One time I had like a 16 students. Another time I had like 12 students. Two times I have done this because I don't take more than 15 students for my course because I keep the limit. This one needs a little bit more of my time when I am teaching, also when I'm in the lab, because lab, they stuck up. I can see every 10 seconds or every minute I see the hand raised, which means I should go to their desk, I should go to their computer, I have to see why are they stuck there, or what mistake, what it is an accidental mistake. It happens, right? In the computation, in the chemistry, even in the research, I say that more than the computer error, the manual error costs the more damage, right? When you're taking the number, if you're taking 68345, right? If you take 68375, that's done. You may think that that's a fourth decimal, third decimal, but that's not right. So they had to know exactly how to enter, because when they're entering the number also in the by hand, they may do some mistake, right? Accidental mistake. So that should be avoided. And when they are doing it, yes, sometimes when they give additional one line space, accidentally they hit the enter button, right? Enter key on the keyboard, the calculation will not run because that line should not be there. Or some calculations, there should be a line required. So this is like these are very small things, but it will make them to not to go further. They get frustrated. That's all, nothing else. I tell them that the frustration is not the solution. So you have to have the patience, and you should just follow the instructions, because when I'm giving the instructions, you do not follow, you get into trouble. So just wait, then it's like a matter of few seconds, fix it, done. It may be like first 3 weeks, a little bit tough. After that, they know the fundamentals. Only thing they need your help and input is on the scientific part. When they do the molecules, when they do some analysis part, that time they need your help. Other than that, they'll be very good. After midterm, it's like so smooth. I tell you, after midterm, they all love this course. They say that, I am ready. I want to do the computation. So I made the students to choose computational chemistry or at least a computation in their research when they moved to PhD. They said, yes, I want to do. It will be part of it. When they do the experiment, they do that one. Now I started encouraging them to do the same way, like start using Python, start using R. I more recommend the biologist to go for R, chemist and physicist to go for Python, because that's what mostly they need. The chemistry students also can use R, but for them, Python is much more better than R. So I introduced them during summer program. They really like it, the basics of this Pythons and how to do it. And that is the important tool for them. Even when they go to do experiments in their graduate program, it's not the matter. They may need it. All the students need it in the future. They should know the skills. If they do not know, it will be very hard for them in their graduate program. Any questions? Because this program, I had to mention one more point. My previous program was evaluated by the evaluator. They all gave the excellent feedback when I used this C grade, the gateway, because gateway resource is user friendly, right? So there are many things they don't need to know, and there are many complications were taken out, made their students' life much more easier. They really enjoyed it. They told that that's very good. They really enjoyed. Any questions? Any comments?
All right. Well, thanks, Tina.
Okay. You're welcome. Okay.
Really good and great for the students to be able to use those tools without too much frustration.
Yeah.
So anybody else have any last thoughts or questions? Like I said, this is our last webinar for this series, but we will be doing other webinar series coming in the fall and other activities with the project as well. So we'll keep you all updated on our mailing list.
We have a question in the chat.
Yeah, I have one question in the chat. What about access to other user-friendly platforms? There are visualization packages available. Yeah, Galaxy. That's a good point. If you are really interested on Galaxy, my colleague biology department will introduce that in the probably next semester. He is the one with me created the introduction to computational biology and bioinformatics. Use the Galaxy for his course. And for me, more of the visualization package, there are open source visualization package called Avogadro. Students can download and use it. But they can't run the calculations using that, but they can just draw the molecules, visualize the molecules, but running calculations, no. But there are open source softwares like NWChem and Gamers, but there are not much of the development after that. But NWChem still they're going under development, but not the Windows based, because those are called Linux based, and you should install the Linux based. Definitely, it won't be the user friendly. Any possible limitations for wider use of C grade, etc., among other institutions? Limitations. One thing I don't know right now. The C grade, it might be working or might not be working, because a person who is maintaining these gateways, if that person moves away from that institution, then that may not work. So You can check, as Linda put that Science Gateways link. You can check where you can get and what resource you can get. Then if there is a support for you, you can always contact the person, because that Gateways resource persons are really good, and they can customize for you, right? Some of them are easy to customize. They have a person available. They can customize for you. That's a great question, actually, what you asked. The next question, do students come to CHPC more in the background, or do they simply stick with the graphical interface? That's a great question. Again, the students, with my experience, 1 or 2 students really wanted to know what's going on behind, right? But not always all. Some of them are, I'm happy. What I got is, it's very easy, user-friendly. I submitted the calculation. I got what I wanted. I prepared my lab report, submitted, done. There are some students always come, like, I want to know, this is so interesting. I don't know, how is it working? How is the calculation running? Then I look, okay, you show the interest, come to my lab. Right? So I take the students to my research lab and show them, how is it working? How do we submit? This is the way. And the students once got inspired. Those students, they said, I want to work with you for your research. I want to work with you for undergraduate research. I said, okay, you're welcome. Come on. Because undergraduate research students, supporting them is much more easier than graduate students. If I have 2 months of graduate student money, I can support 1 student for the whole semester, right? Because graduate student stipend is much more expensive than undergraduate students. So it's easy. That's a great question, actually. Those students who wanted to see what's going on behind, they ended up in my lab as a research student. So after that, they ended up in the lab. They got a co-author publications, and they also went to PhD in computer science, computational chemistry. Chemistry, I want to do the computational chemistry or computational material science. That's what they have done. Okay, the recent questions are very, very important questions. Very nice. Thank you for that. Excellent questions. I didn't know how to convey that one within my presentation, but those questions makes me to tell the story very well. Thank you. Thank you all for your patience, and it's very good to see you all on Friday, and we will meet sometime in person. Thank you.
Thank you.
Thanks, everybody. Have a good weekend.
Thank you. Bye.